Okay, hello calculus students. Our first set of notes for tonight are local linearity, and I highly recommend you stop the video periodically to write and then listen to me. As we talked about in class, hopefully the more active you are with your notes, like if you stop periodically and think like, oh, do I actually know what she's talking about? Let me summarize for myself. What did I just write down? What does it mean? The better it will stick in your memory. All right, so for any smooth graph, right? So no sharp points, like no absolute value functions, for example. When you zoom in, the graph is going to look linear. We did in class a sine function or a transformation of a sine function, and I'm highlighting with the orange where we zoomed in on. And this is a little different maybe from the one we did in class, but it's the same idea. Once we zoomed in and zoomed in and zoomed in, maybe I fooled you and it looked linear, which is not really a fooling you. It's just an aspect of functions. If you zoom in really close, functions mimic linear behavior. So that's the original function, this whole sine graph of some form or cosine, whatever. When I zoom in, that particular portion looks linear. This is the big point. I'm not writing this down somewhere, but well, I wrote it down later, but the big point is that allows us to get a really good approximation of instantaneous rates of change. All right, just a note for the future you, if I have an absolute value function, no matter how much I zoom in on this sharp point, I'm never going to be have local linearity. So the zooming in and the local linearity are only for smooth graphs. All right. As I just said, and I want you to have in your notes, local linearity allows us to use two really close points on any function, and then we can approximate the instantaneous rate of change at any point in the original function. Sometimes it's going to happen, or it happens in real life, you can't actually get the exact value that you want, so you need an approximation. All right? We didn't talk about this in class, but we're going to talk about this a lot coming up, so let's get it in your notes. My original function is this black form. Let's say some sort of function f of x, all right? If I can think of having a line over here that just touches the point xy on the function in one point, right? Then the slope of that pink line is the exact value of the instantaneous rate of change. You need to stop the video and think about or repeat what I just said. That's important. If I can get a line here, whatever it's called, and it touches my original function just in one point, the slope of this line is exactly the instantaneous rate of change. Okay? What we did in class and what you're doing for homework is we're approximating it. Do you see I have 2 points on my black function? I have 2 points. They're on my function, but they're so close together, they might as well basically be 1 point. But I have function information. I got x1, y1, x2, y2. I can approximate what I really want to know by finding this slope. All right, so that's this first page of your notes. Can I do this? Oh, I can't do that. So let me go back here and get page 2. All right. So the second page of your 3 pages of notes, 2 important definitions we're going to talk about all year. Mostly this one, but this is nice for approximation. A tangent line, that's what I'm defining. A tangent line to a graph is at the point I'm interested in, it touches it in one place. Now, I can't rotate that line 360 degrees like, do you see what I'm doing here? Oh, look, I touched in one place. No, I have to mimic what's the movement of the graph. So I'm mimicking the rate of change here. So that tangent line that in this way touches the graph in one point, we'll talk about it more as the year goes on. This pink line is the tangent line to my original function. If my function is black, same function, but I pick 2 points on my function, not just this one point. If I pick 2 points on the function, this point, and I connect the line between them, that's a secant line. All right, you'll notice tangent and secant are trig functions from pre-calculus. They're not used in the same context here. They're called this because it's a relationship that we won't go into, but it's kind of a cool relationship. But in our context, secant line means a line that touches my original function in 2 points, and a tangent is a touch in 1 point. Okay, so tangent line, secant line. And just to say it again, we can summarize, we can approximate the slope of the tangent line, which is what I really want, the instantaneous rate of change. We can approximate it by finding the slope of the secant line. All right, so you might stop the video, close your notes, and see if, what did I talk about so far. All right, the next thing I want in your notes is this bottom graph over here. In class, we did x squared with our local linearity. Your homework was to do x cubed and x to the 4th. These are the graphs of the function. Do whatever your homework is, but can you start 2 columns here? I want to plot the slopes of the tangent lines, or the instantaneous rates of change, because that's what it is. It's instantaneous rate of change at your special points. We'll fill in these 2 columns in class. All right, I'm going to start another video to get your 3rd page of notes.